Hello.
Nothing.
Hello, and let's get started. Welcome to our ninth series of customer webinars. Hello, and welcome to the ninth in the series of our customer webinars. The topic for today's webinar would be on reverse power flow, its effect on transformers, and the potential solutions. This webinar is presented by Hakan Sahin, who is our Corporate Director of Business Excellence. This webinar is being recorded, and it will be available on our website, and this will also go on YouTube as well, where it will be available for future viewing. If you have any issues in getting a link to the webinar recording, you can always reach out to the marketing email ID in the invite, and we will link you up accordingly. I will now invite Hakan to take over and provide us this presentation on this subject.
Thank you, Rajiv, and thank you everyone for joining our webinar today. As always, I would like to start with a safety moment. A safety pause will help all of us become more safer in our daily lives and in our operations. Pause before you start, assess the possible hazards, understand how to proceed safely, share your plans with others, and execute activity safely. In today's presentation, we're going to talk about reverse power and its effect on transformers, and maybe some potential solutions. So I want to start talking a little bit about what reverse power flow is. And not only this slide, but the next 3-4 slides is going to try to explain this phenomenon. But where does it come from? With increasing levels of distributed renewable energy being brought online, many electric utilities are having to find effective ways to keep the distribution network stable while power is flowing in the reverse direction. As I said, during this presentation, we'll discuss what it is and how it affects our transformers and potential resolutions. Traditional power system network was designed for accepting power flow from generation to load via transmission and distribution networks. With the shift in the global demand for energy, the traditional power system as we know it is shifting its dynamics to accommodate the renewable energy resources. The penetration of the distributed energy resources, DERs, on distribution and transmission networks is disrupting the traditional power flow to become bidirectional. A reversal of the traditional power flow from distribution to transmission system by too much distributed energy resources penetration is referred to as the reverse power flow. Due to highly unpredictable nature of such variable renewable energy sources, in many circumstances, the instantaneous power demand and the supply do not always match, and insufficient energy storage capacity at the DER generation nodes leads to reverse power flow towards the grid. Okay, now let's look at the difference between traditional versus modern electrical power grids. In the traditional grid, everything starts from generation, unidirectional power flow into transmission. From there goes into distribution, stations, lines, and all the way to the load. Everything is one direction, unidirectional power flow. But with the renewable energy sources being added to the distribution grid, as we can see here, the result is that the energy being generated at certain times of the day and the amount of locally generated power can exceed the local load, which can result in the flow of the power back towards the substations. So if you look at the direction of these arrows, once again, it starts from generation, unidirectional going into transmission. However, as I said before, due to this power generated within the renewable energy sources or the battery stations and not being able to store, this energy can actually, or do, not just can, but do flow in the reverse direction back into the transmission and to and back from the smart load as well. Couple high-level notes on the impact of reverse power flow on our transformers. The pictures here, which I'm sure everyone here has seen some of these in real life, but some bulk electricity generations in wind and solar. And this market is growing and growing and growing in our country and around the globe. In our country, the wind reflects around 539 gigawatts of energy, and the solar is 403 gigawatts of energy markets. These are the two largest renewable energy sources, sharing the majority of new renewable generating capacity globally. Couple questions that comes to everybody's minds. One, does reverse power flow impact the performance of existing transformers and LTCs in the grid? Two, does it make sense to replace interface transformer using customized design to minimize restrictions on reverse power flow impact? Now, even though I made a note here about the LTC, but because we are not an LTC manufacturer, our presentation here is mainly going to focus on the impact, effects, and the resolutions from a transformer point of view. However, LTCs and regulation is going to play a role in the possible solutions and resolutions discussions. Integration into the existing system. The wide range of generation capacities and the unpredictable amount of energy generation limits the decision making for utilities and system operators. Our utilities have large capital investments. Renewable developers would like to see maximum energy production achieved to minimize payback periods. However, everything has to balance itself. Under lower demand periods, utilities and grid operators reject the renewable energy fed back to the grid. The integration of the highly penetrated renewable into the energy systems also require an asset management study. The operation of power system components is affected by such integrations. Therefore, the modifications of power purchase agreements like policies, standards, market and regulatory frameworks to effectively harness the benefits that can be derived from renewables while ensuring system reliability and security of the supply. In the next several slides, we're gonna look at, from an electrical calculation methods point of view, how reverse power actually occurs in the systems and the distribution networks. The energy transfer through interconnect transformer is represented as two-part network, as you can see here, in which there are two impedances, the short circuit and the magnetizing. The input port is connected to the grid, and the output port is connected to the load generation. The primary and secondary short circuit impedance are represented, as you can see, in the middle of the slide. I just want to make a little note here. Starting with this slide, the next several slides will have some formulas in it, some circuit diagrams. However, within the limited time we are given in this webinar, our focus is really given the methodology and the basic understanding of where the reverse power flow is coming from and going into how it affects our transformers. So if you have any questions at the end that you want to continue this discussion, we are going to give an email address where you can get in touch with us, and we can have separate discussions if we wanted to get a little deeper into these calculation methods and formulas. So when we look at this slide here, the magnitude of maximum power transfer is defined by terminal voltages, V1 and V2. Also, the difference in terminal voltages V1 and V2 in terms of magnitude and the phase angle represents the voltage drop in the transformer, which is derived through short circuit impedance Z, %Z, and the load currents. Consider the load terminal of this figure drawing current or injecting current to the grid at unity power factor. Let's start looking into transformer operation for quadrants. Let me clarify something here. When we say transformer operation for quadrants, we are not actually talking about transformer operating differently, absolutely not. But what we are talking about is the 4-quadrant energy flow back and forth from the transformer and how we can mathematically see these affecting our transformers. The 3 scenarios represented below here, where we considered the I2 as the load current and I2 prime as the generation current, and the voltage drop across the transformer short circuit impedance, creating a phase displacement between V1 and V2 as shown below. So when we look at these 3 figures, which we will talk more about these figures in the next coming slide, is on the figure A, we are looking at a similar excitation and magnetization, which is E2. So I want to take a little pause between each of these figures. And when we look at B, the similar load voltage V2, and the C, the vector representation of transformer forward and reverse power flow at unity power factor with similar grid voltage, which is V1. As I said, let's look at these 3 figures, and then we're going to go into next slide where we will talk a little bit more deeper about these 3 figures. Continuing on understanding the 3 figures, for all 3 cases demonstrated and we looked at in the previous slide, A, B, and C, the positive values of phase replacement draws power from the grid, and negative values will inject power to the grid. The excitation voltage E is maintained in A to maintain magnetic performance of the transformer core, which necessitates the increase in injection voltage and decrease in receiving grid voltage. The second scenario, B, where the injection voltage V2 is maintained and both excitation and grid voltage are decreased. The third scenario, C, is applied to the infinite bus where the grid voltage is constant and the injection voltage V2 and the magnetization voltage E of the transformer are increased. The magnetizing flux density of the core increases in this case. So here comes the 4 quadrants. Once again, as I was saying, it's not transformer operating in 4 quadrants, but it is really the 4 different power flow scenarios classified as 4 quadrants, as we are showing here in this picture, depending on the energy source or the energy storage, how that is flowing the positive versus negative energy flow, or basically the direction of the energy flow. Normally, the electricity utilization and generation involve the reactive power flow back and forth from the grid to the load centers for power factor improvements and the voltage regulations. In this crowded slide here, we're going to touch base with each of these quadrants. And once again, the quadrant is basically description of the power factor of the system, which defines the flow direction of the energy. But before I start talking a little bit about each quadrant here, I want to remind everyone again, whoever wants to get a copy of these slides, please email to the marketing email that we will share once again. It's the same email that you registered basically to this webinar. Please email to that, and then we'll be more than happy to share this presentation with you, because there is quite a bit of technical information here that will be very helpful for for everyone to go back and read when necessary if needed. Having said that, coming back to the four quadrants, Q1. Q1 is the nominal load with inductive kVAR demand. As an example, motors. Motors are a good example of this Q1 operation here. Usually, motors draw lagging reactive power, which is considered as, you can see here, plus P and plus Q. The active power flows from grid to the load with the phase displacement greater than 0. And the magnetizing voltage E is greater than V2. And the magnetizing current IM is drawn from the current grid. When we look at the second quadrant, the DER, which is the distributed energy resource, generation with inductive kVAR demand. Okay, as an example, wind. The induction generators, coupled with the wind turbines, are the induction generators which delivers active power and absorbs the inductive reactive power from the grid, creating a negative P, but with still a positive Q. The active power flows from DER to the grid with phase displacement less than 0. E is still greater than V2, so the magnetizing current IM is drawn from the grid. When we look at Q3, this is the distributed energy resource DER with capacitive kVAR. As an example, solar with cap banks. The solar farms or the distributed solar generation includes the capacitive banks for the load balancing over time. This capacitive bank and solar panel deliver active and reactive power to the grid, which is minus P and minus Q. The active power flows from DER to the grid with the phase displacement less than 0. Now this time, the E, magnetizing voltage, is less than V2, and the magnetizing current IM is supplied by DER at the load terminal. Last but not least, the fourth quadrant, load with capacitive kVAR. As an example, voltage regulators. Usually, capacitive banks are used to boost the load voltage and compensate line drops in the system. They are normal resistive loads, and they deliver reactive power to the grid, causing a plus P and negative Q. The active power flows from grid to the load with greater than 0 phase displacement, and this time, again, just like Q3, the V2 is greater than E, and the magnetizing current is supplied by the DER at the load terminal. Having now given the basics behind why and how there is reverse power flow, now we are going to start talking about how does this affect our transformers? What does it do to a transformer, if anything? Is it really that scary or not? But what is it? However, before we could get into the transformers topic, we all needed to understand the basics from where the reverse power is coming. The life expectancy of a transformer varies depending on many factors: temperature, dielectrics, loading, faults. And aging transformers are potentially subject to an increased risk of failures, as we know. In our country, the average age of all transformers in the distribution interconnecting systems are around 40, 45 years, which most of us, I'm sure, know. So when we think about the effects of reverse power, there is an immediate need to study the impact of the reverse power on transformers, because we've seen now what reverse power is and how it will affect the magnetizing currents and the voltages. Now we're going to talk how that describes into a transformer performance. As we described earlier, the magnetizing flux in the transformer core is established through excitation voltage E, which is derived for all four quadrants of operation as we described before. So remembering the four quadrants, the Q1 and Q2, the core excitation is delivered by grid, and for Q3 and Q4, the excitation is delivered by the distributed energy resource. Now, considering the grid per unit voltage is constant, the excitation voltages for Q3 and Q4 is always higher than design values, which increases the core flux density under those scenarios. The operation of these four quadrants are transformed to the rated active power, forward positive and reverse negative, and with reactive power ranging from -8 lagging to +8 leading, the load voltage V2 for substation transformers are usually set 5% higher to compensate for voltage drop on the feeder. The transformers are optimally designed closer to the knee point of the magnetizing curve of the core. Therefore, with small increase in excitation voltage, E, the magnetizing current and magnetic losses increase significantly. And this is where now we are going to get into the effects of transformers. However, before we can start talking about how reverse power can affect our transformers, we needed to understand to a basic level to how the reverse power is occurring today in our modern grids. So far, we have, as a summary, we have seen one of the basic effects of reverse power is talking about the excitation and the magnetization of our transformers. Magnetization meaning, for those of us, hopefully everyone on this call knows the basic operation of transformer is by mutual coupling, an excitation from one winding to another, and the core becoming a big magnet. Usually, the magnetizing current is very low for transformers. Twofold increase will not really cause any issues. However, the increased core losses will impact the thermal and hence the life of the transformers. As we all know, the major effects of temperature increase in transformer is the life of the insulation, which is why our transformers are designed to run at 65 degrees C with the average ambient that comes close to 100 degrees, where the cellulosic material, paper, wood that we use inside will start aging faster. That's why keeping the temperature under control in transformer is very important. And aged insulation means the transformer's integrity against short circuits, faults, will have degraded as well. Temperature is a very critical phenomenon for the life of the transformer. Combine that with moisture and other effects, we are basically talking about the life expectancy of a transformer. So when we look at a typical core form type transformer having 3 limbs, as we show here on the side picture, we don't really, this 3-limb structure doesn't really provide a zero sequence flux path. So the reverse power flow can increase the magnetizing current and the core losses. A couple additional notes on the core performance and core design for the transformer that we were just talking about on the previous slide. The temperature rise limit for core per the IEEE standards is 130 degrees C. And the cores are designed to run at 105% plus load plus the 0.8 power factor. Another additional note is the cores that we design are designed, or the transformer cores that we design is designed to run at 110% of the rated voltage under no load operation. Once again, under no load operation. But who uses transformers only for no load operation in the field? Transformers are there to supply the load, which takes it back to 105% plus load and plus the 0.8 power factor. Having said that, the optimized low-cost design with higher flux density and higher short-circuit impedance may have more variation in the magnetizing currents and the core losses. If grid voltage is maintained, then the excitation current is further be increased and the core is saturated. The saturated core further develops the harmonics and losses associated with it. Normally, infinite bus voltage V1 at the grid terminal is maintained, resulting in further increase of magnetizing voltage. Also, the shape of the magnetizing current becomes non-sinusoidal and contains significant total harmonics distortions, THD. Now, under our IEEE standard C57110, there are calculation methods and descriptions for the non-sinusoidal conditions. The increase in THD, the total harmonics distortions, leads to higher core losses. The core also saturates if the voltage increases beyond the operational limits. You know, when you try to pass 115% of no load voltage, or you start passing that 105% with load and power factor, the cores are not designed to go beyond the limits that they are designed for. If the power flow is maintained in third quadrant, then the increase in temperature reduces the life of the transformer, up to 25% loss of life. If the life of the transformer is required to be maintained, which we always want to do, then the losses are to be maintained for all four quadrants that we saw several slides ago, as per the nominal design. Therefore, some utility companies impose certain restrictions on developers, manufacturers, service providers, and distributors for reverse power flow through the interconnect transformers like substation transformers and distribution transformers. Hey, now that we scared everyone so much about reverse power flow, let's start talking a little bit about potential resolutions. Life is coming to an end, all the transformers are going to blow up in the field. Absolutely not. When there is a problem, there is a solution. So let's start looking into the resolutions. The additional network stresses described above ultimately manifest themselves as stress on the substation, collector, and generation step-up GSU transformers in the forms of increased losses from 1, oversaturation from line or load side over voltage, and 2, increased voltage harmonics from the load supply. These stresses will prematurely age the life of the transformer dependent on their amplitude and quantity. Fortunately, transformer manufacturers like ourselves, we have the experience in design to resist these types of stresses when the system characteristics are known. Let me underline that one more time. When the system characteristics are known. Techniques such as increased steps for on-load tap changers, full load voltage regulators, or reducing the flux densities, we may use these to prevent overvoltage saturations. Integrated inductors and increased K-factor designs can also support on reducing the harmonic stresses on transformers as well. Today's challenge is that the levels of increased voltage and voltage harmonics caused by reverse power flow have been mostly not communicated or not considered in transformer specifications. This is okay, as our systems are developing with the new renewable energy resources. As we spoke at the very beginning of this presentation, we are changing from traditional to modern. That means we are learning, and as we learn, we are adapting ourselves, our transformer specifications, materials, and we will design and we will build transformers to overcome these additional stresses coming from the reverse power flow. However, a system study of the network that accounts for reverse power flow will help improve transformer specifications so that manufacturers like ourselves can account for and improve transformer design for the long-term and reliable power distribution. As an intermediate step to address already installed units, digital technologies to monitor for total harmonic distortion and primary and secondary voltage at the transformer can be installed in order to get better predictability of potential failures and increase aging characteristics. So these are some of the solutions for the existing fleet out on in the field. Before we start looking into these 7 points of conclusion, so let's get our summary together about reverse power. What did we talk about in these slides? How does it affect core form transformer? And we will talk about each point here. Now we know where the reverse power is coming from, power flow. Now we know how it's affecting the excitation and magnetization of the transformer. And we also discussed about how that may affect the transformer. So everything in a summary, conclusions in this slide for your future use. Number one, the phenomena of reverse power flow impact the transformer performance of the interconnected transformers. It is a phenomenon. The transformer losses, core and harmonic, are significantly increasing even at 15% higher excitations. Once again, as a reminder, transformers are designed, most transformers are designed to run at 110% with no load, 105% higher excitation with load and the 0.8 power factor. Number three, for any design, reverse active and reactive power flow conditions in Q3 observes the maximum core losses for any load condition. 4, if the reverse power flow is not restricted, then the interconnect transformer loses its life by almost 25%. 5, the restriction on power factor of reverse power flow can maintain the life of the transformer. 6, the amount of impact on transformer life depends on design of the transformer and operating conditions. So let's underline number 6 a little bit more. The amount of impact on transformer life. So obviously, if the reverse power flow is not controlled, it is going to impact our transformers. However, if we know how much that's going to be, but some utility customers may come and say, I may not know that either, because depending on the load, depending on the generation, and depending on the usage, that we may not know, then we are going to have to estimate between our utility customers and the renewable energy suppliers. If we can get a number that estimates it, then of course we can design the transformers and we can get the materials needed and build the transformers for these operating conditions. Number 7, system studies that account for overvoltage and increased harmonics caused by reverse power flow can be used to improve transformer specifications and design. And let's not forget, when we talk about increasing excitation in transformers, I'm sure most of you on this webinar knows, increasing excitation means increasing sound level. The transformer has no load noise and load noise, especially for larger transformers. But the main source for small and medium power transformers, the main source of sound is the core. When the excitation of the core starts going beyond the design limits, then the core, as it gets starting to get towards its limits, the sound level will increase tremendously. So these are 7 of the main conclusions that I wanted to note down for our presentation today. In closing, thank you so much for attending to our webinar today. As we said at the beginning of our slides, if you have any further questions, if you would like to discuss this topic or any other transformer related topic with us, offsite, please email to sales@vatransformer.com email, as you can see in this slide. Thank you. Thank you so much. Jana, do we have any questions from the attendees? No questions.
Oh, yes.
There is one?
Yes. Can you talk about the problems of reverse power on a delta WYE system?
Delta Y system? Yeah, sure. Here with us, I have our manager for development engineering team, Bala. So I would like him to answer the upcoming questions. Bala, would you like to take that?
So either it is delta or Y. When it comes for a transformer, the reverse power flow effect will be depends on the design. Say, for example, if the core flux density is designed at 1.74, as Hakan explained, 15% increase in voltage in Q3 in the quadrant 3 or 4 will put us very close to saturation level, close to 2 Tesla. And the saturation limit is approximately 2.03 Tesla for magnetic material. So that's where you have the core will start drawing more amount of harmonics, and that will have associated issues, problems, and the heating, and also the sound. You know, if you the third harmonic will add up the flux, and it will saturate, and the vibration will increase. So it is either delta or Y, irrespective of that, the voltage increase will determine how it impacts the transformer.
So basically, Bala, what you're saying is, regardless if it's delta Y or delta delta, YY, the effect is really related to the increase in the excitation in the core.
Yes, and there will be some difference when it comes to the impedance for the zero sequence, which is third harmonic.
Yep.
That will play a role, but that will change based on the delta and Y, and that again depends on the transformer design, how it is designed. For example, if you take an example of a delta connected inner winding, your zero sequence reactance is lesser than positive sequence, and if you have the delta is outside, it is different. They are not same. They are not reciprocal as in the case of a positive sequence.
Very good.
Is there anything that can be done to mitigate these problems on an existing transformer, or is replacement the only good option?
I'll take that. Actually, the answer to this question is already discussed in some of the slides before. There are some regulators that can be put in, some digital circuits. Replacement, I don't know if I want to get to that level, but the voltage regulated distribution transformers are an effective measure, as we stated in one of our slides previously. So when you obtain the copy, that is in the conclusions of reverse power, is one of our solutions that's recommended by the experts.
Do you manufacture delta zigzag transformers?
Yes, of course we do.
Yeah, we have done for utilities.
Yes. These are the only questions? Well, since we have a couple more minutes, maybe I have some questions that I would like to challenge Bala here, if it's okay with everybody, just in case if some of our attendees would like to ask also, and these are some of the questions that I had in my mind. I'll start with this one here. How can you control the amount of magnetizing current in a core form transformer, Bala?
So the magnetizing current is the current, is required for the flux to flow in the core, which means that it is the magnetic energy required for the core to act as an coupling medium. So if we design our transformer at 1.5 Tesla, as we know, the transformer behavior is nonlinear. You have a BH relationship, and then you have watts per pound relationship. Everything follows a nonlinear relationship. So the control comes at what what flux density you are designing at. So if your transformer is designed at 1.5 Tesla, most probably your reverse power flow will not affect your transformer. And if your design is at 1.72, then you are going to see some issues what we discussed in this presentation, such as increased losses, then temperature will increase, then you have a reduced life, which will be very difficult to predict because of the different component of harmonics which core is going to create, and that again changes based with respect to the material. Core material, you have a M or H type material where you have high quality materials will have kind of lower harmonics than standard materials. So this is how we can control.
Very good. I have one other question. What is the impact of reverse power flow for a transformer operating in the field?
So as this was detailedly explained by you, and the first thing is that the voltage is going to increase, and you said it is 15%, and we don't know whether it is 15 or 10 or 20%, and the impact of that will be determined by your own design and the flux density of the transformer which is operating. Like I was explaining, if it is already designed lower, then we may not see any issue, and if it is designed at higher flux density, then you will see all the issues.
Very good. Any other questions? Well, once again, everyone, thank you so much for attending our webinar today. Our webinars are going to continue. Appreciate your business, appreciate everything you do for our industry.
Yeah, and this is Rajiv. Again, thank you all for your participation, and I want to again remind you that this webinar is eligible for CEU credits, and if you would like a continuing education credit certificate to be mailed to you, please send us a request on the marketing email ID you see in the invite, and we will provide the same. And as the team here mentioned, a copy of the webinar will be available on YouTube as well. Okay, thank you.
You have a question?
I do have another question.
Oh, you do have another question. All right.
Sure, we'll take it.
For it.
If we can assure that we only operate in Q1 and Q2, where bars, BAR, are always flowing towards distribution, is there a concern as long as transmission stays below 105% and TR 0.8% power factor?
I think if we are in the quadrant 1 and 2, I don't think any issue we will see from the existing transformer, because where you have a Q is flowing from to the load.
Yeah.
So,
but then the major question comes, if we can assure, just like our attendees say, if we can assure that, yes, the impact will be less. One more? All right, that's good.
I don't know. What about large capacitors on the secondary of transformers in reverse power mode? Does this add to overvoltage issues?
Absolutely.
Capacitors obviously will have core voltage problems, and then that will bring us the additional voltage to the transformer, which again, going back to the same issue of core problems where you will see additional losses and harmonics.
Okay. Please define reverse power flow in more detail. Do you mean from high voltage terminals to the from low voltage terminals to the high voltage terminals?
Oh, no, not at all. Reverse power is basically energy, electrical energy flow from the distribution system, just like in our slide number 6, from distribution back into the transmission line, from wind and solar generations, depend on the, as I said in my presentation, depend on the time. Sometimes the wind and solar generation stations produce so much energy that the load is not needed. So then that energy comes back to the distribution system. Versus before we had these renewable energies, it was from generation to transmission through distribution to the load. But now we have additional generation stations. So consider this, we used to have only one generation. Now we have the generation, which is the traditional generation, but we also have other generations that are tied into the grid, such as solar, wind, and even battery stations, because they charge and discharge. So no, the answer is not the reverse power. We are not talking about within the transformer itself. It's not from one winding to another winding. It's basically within the grid of the energy flow direction.
I think this goes back to the, does this add to overvoltage issues? Would a tertiary winding help?
Go ahead, Paula.
Tertiary winding. Tertiary winding is a delta connected winding which solves the problem of when you have Y connected unit, you need to add a tertiary winding for third harmonics to flow. And in US, especially if you have HV and LV both are Y, we don't build without delta connected tertiary. Yep. And it is only done maybe 1-2 MVA small ratings, but this will only solve the problem of zero sequence. It allows the path to flow, but voltage increase in its terminal will really change your V by T of the design, volts per turn. So that is not solved. So the delta connected tertiary winding, it will act as either a stabilizing winding, providing path for third harmonic, which is a zero sequence. So they may reduce the effect, which I don't know fully now, but it will not fully solve your overall voltage problem.
Yeah, I mean, basically the problem comes down to increasing the excitation of the transformer. That's what reverse power is doing. The tertiary windings are used in transformers really for harmonic stabilizations, like you said, Paolo, on YY or auto transformers. So just putting a delta in a transformer, thinking about the reverse power and saying, okay, let's put a tertiary winding so it's going to help is not really going to help the situation, because the root of the problem is the injection of the energy back into the transformer. Okay, well, very good questions. And once again, thank you all so much for attending our webinar, and we will be doing another one coming up soon in the next month. Thank you.
Thank you all.
Thank you.